we can start.
Okay, so do you all know what complex numbers are? Okay, so I'll just give a quick introduction to what they are. So like, just to make sure everyone's on the same page. So a complex number, so we define I to be the square root of -1. Now clearly this is not an ordinary real number. So so I does not belong to the reals. So what we do is we create the plane of real number, the Cartesian plane, y-axis and x-axis, and we assign every point a comma b to complex number a plus bi. And usually if the point's letter is denoted as z, capital, wait, let's say capital X, no, capital A would be a better example. We denote the complex number with a. In this example, let's use d. So this complex number would be equal to d. Okay. So now complex numbers, there are two components to a complex number. One thing is the distance from the origin, which is by Pythagorean theorem can be easily checked to be root over a square plus b square. And the other is the angle, which is also theta equal to tan inverse of b by a. And now there's a very important theorem which of Leonard Euler, that the complex number e to the I times t is equal to cos of t plus I sine t, which basically means that if you have the complex number with angle t and length 1, this thing will be e to the I t. Is everyone fine with this?
Yes.
Okay, good. So, now every complex number, let's say this complex number is z, or wait, we've denoted it by d. We denote its reflection across the x-axis as d conjugate. Now, because the x value is preserved and the y value becomes negative of the original thing, b conjugate is equal to a minus bi. Okay, so we have this for any complex number z equals to a plus bi. We have that z times z conjugate is equal to a square plus b square. This is because z conjugate is equal to a minus bi, and then z z times z conjugate becomes a square minus bi whole squared, and I squared is -1 because of this. So this gives us a very powerful property that when z, so we have this thing called the unit circle. The unit circle is a circle of radius 1 around the origin. And now the thing is, whenever z is a point on the unit circle, we have that z conjugate is equal to 1 over z. This is because on the unit circle, if z equal to a plus bi is on the unit circle, we have the root over a square plus b square is equal to 1, since the distance from the origin is 1. And this gives the property that z conjugate is equal to 1 by z on the unit circle. And this is a very powerful property since almost everywhere, many places in complex numbers, a z conjugate comes up. And when we set the setup to have many stuff on the unit circle, this becomes way simpler, way easier to use. Okay, so now I'll move on to a few formulas. So before I move on to formulas, let's say we have the segment B, A, E, and C, D. Now, oh, I will show now these segments will be parallel. So we have that AB is parallel to CD when the complex numbers, when B minus A by C minus D is a real number. And this is because because one very common thing you want to do in complex numbers is treat everything like a vector. So c minus d represents sort of like the vector going from d to c, and the complex number b minus a represents the complex number of the vector from a to b. So uh, if these two segments are parallel, we should have that these vectors have the same angle. And if now we call the angle of a complex number this the argument of the complex number. So we want that argument of c minus d is equal to the argument of b minus a. And if this is equal to theta, we have that we know by Euler's theorem that every complex number is r into e to the I theta, where r is its magnitude and theta is its argument.
But
So if these two have the same argument, and this is and c minus d is equal c minus d, we denote the magnitude by with these brackets is r1, and magnitude of b minus a is equal to r2. We get that b minus b minus a is equal to r2 into e to the I theta, and c minus d is equal to r1 into e to the I theta also. And this means that the ratio is a real number. So we have this. Now one property is, we go back to our diagram, we can see that a number is a real number if and only if its conjugate is equal to itself. So any other real number, any other complex number, its conjugate will not be equal to itself. But for any real number, the conjugate of that complex number is equal to itself. So, and also know that an important property is, we have few important properties. So let me do it in a different color. We have w plus z, its conjugate is equal to the conjugate of w plus the conjugate of z. And same can be checked with subtraction, multiplication, and division. So basically, the conjugate function distributes over stuff like addition, multiplication, subtraction, and division. Oopsies.
Atharv, I have a question. Like, how do you actually define AB and CD in terms of the two lines?
Oh, so A is the complex coordinate of the point. So A has complex coordinates A. B has complex coordinates B.
Ah,
Okay.
okay.
So we get that AB is parallel to CD if and only if B minus A times C minus D, its conjugate is equal to B minus A by C minus D. Okay. Now another thing, if you notice over here, if a complex number, its conjugate is equal to, let's say this complex number is Z, and Z conjugate is equal to negative Z, this would imply that Z is pure imaginary. Meaning, like, if Z is equal to A plus BI, a pure imaginary number is where A is equal to 0 and B is a real number. So uh so now we do similarly to this with perpendicular. I won't go over all the details, but we have that if BA is perpendicular CD, we will get that BA is perpendicular to CD if and only if A minus B by C minus D, the conjugate of this is equal to B minus A by C minus D. And it's the exact same thing as before. We do all of these things to get that if two segments are perpendicular, the vectors of the difference of the segments, the ratio should be a pure imaginary number. So is this fine with everyone before we move on to the problems?
Yeah, sure.
yes.
Nice. Okay. So now firstly I'll show some key properties of the unit circle. the most powerful property of the unit circle, which I've already talked about before, is that for anything on the unit circle, we have that z conjugate is equal to 1 over z. So, um, so now let's see what it means for, let's say we have the unit circle and we have 2 points A, B, X, Y. Let's see what it means for AB to be perpendicular to XY. So now we get that AB perpendicular to XY gives that A minus B by X minus Y. Its conjugate should be equal to negative of A minus B by X minus Y. Now, we know that the conjugate of A minus B by X minus Y, since conjugates distribute over these functions, will become conjugate of A minus conjugate of B by conjugate of X minus conjugate of Y is equal to B minus A by X minus Y. Is this fine with everyone?
Can we not just cancel x minus y from both sides?
No, we can't, because this is a conjugate.
No, like the denominator is the same, right?
No, it's not the same thing. This is a conjugated version.
Oh, okay, it wasn't written up.
Yeah. So now we know that A, B, X, and Y are on the unit circle. So by this property, we get that 1 by A minus 1 by B by 1 by X minus 1 by Y is equal to B minus A by X minus Y. So this gives us that B minus A by BA by Y minus X by XY is equal to B minus A by X minus Y. Now, if we cancel the B minus A from here, we get that XY by Y minus X times BA is equal to 1 by X minus Y. Now, if we do some more algebraic manipulation from here, we get that XY plus AB is equal to 0. So this is what it means for two segments on the unit circle to be perpendicular. Is everyone fine with this? Since this will be very important in later on.
Yes.
Okay. Anyone else? Any doubts?
It is clear.
Good. Now I show the formulas for like some well-known stuff. So firstly, let's say we have a segment AB on the unit circle, and we have some random point X. Now we want to find the foot of the perpendicular on AB from X. So for this, I won't exactly be proving this, but the formula will be 1 by B would be equal to 1 by 2 times A plus B plus X minus AB, the conjugate of X. And now, one special way you can remember this is that say you have a triangle, say X is on the unit circle. Now, we drop this perpendicular here, and we know that this point, I've already used P. Let's say K is equal to negative AB by X because of this. Oh, also, I forgot to mention one theorem, which I will prove later on. Let's say you have A, B, and C, and these points are on the unit circle. Then the orthos center of these points, H, has coordinates H equal to A plus B plus C. Is that fine with everyone? I'll prove this later.
Yes.
So now say we want to calculate this point, right? And if this ortho center we know has coordinates a plus b plus x. And now it's a fairly known theorem that let's say you have a triangle and a circumcircle, and its ortho center is here, and this point is the midpoint of the ortho center and the intersection, where this is the perpendicular. So we get that this foot, which is meant to be P, we get P is equal to A plus B plus X, which is the ortho center, and this point's midpoint, minus AB by X by P. And we know that since X is on the unit circle, we get that this is equal to A plus B plus X minus AB into X conjugate by 2. So this is a way you could remember it. Just try deriving it for the case of the unit circle, and yeah. Is this fine with everyone?
Yeah.
Okay.
Yes.
So now we derive the coordinates of the orthocenter. So now there's two ways you could derive the ways of the orthocenter. One which I'll not be doing and one which I will be doing in class. Now one thing is we have A, B, C. Now the definition of the orthocenter is the intersection of the altitudes, right? So we get this is to be, let's say, as H. Now we could, oh wait, also we're assuming that this is all on the unit circle. Now there's one thing we could do, which is like the most bassy way to do it, is know that AH is perpendicular to BC, right? So we constantly use this to get 3 different linear equations in terms of H and H conjugate. And then we solve for H. But the way I'll be doing is, we know that the reflection of H across the midpoint is equal to the point diametrically opposite to A on the unit circle. And now, can anyone tell me the coordinates of the point diametrically opposite to A on the unit circle?
Minus A.
Yes. So we have that H plus of minus A by 2. The midpoint of H and minus A is equal to the midpoint of B and C, which then gives the H equal to A plus B plus C. Is this fine with everyone?
Yes.
Okay. Now I will cover our first problem. Let me just wait, let me just cover 2-3 more theorems which will help in these problems. Say you have a segment A, B, and a point P. And we're assuming like majority of the times you'll just be assuming that A and B are on the unit circle. So we want to find now know that the foot of we have that P belongs to AB. If the foot of P, the perpendicular from P onto AB is P itself, right? So what I'm saying is, let's say you have AB and P, and the foot of P onto AB is P prime. If P equal to P prime, if and only if P is on AB. So with this will actually give us an equation to tell if a point P is on the chord AB of the unit circle. We get that P belongs to AB if and only if P is equal to 1 by 2 times A plus B plus P minus AB times the conjugate of P. And if we move stuff around, we get that A plus B is equal to P plus AB times B's conjugate, which is very powerful actually. And one notable thing we can do is we can plug A equal to B. So in this case, we get that if this is the unit circle and this is the tangent at A, and this is the complex ordinate of P, we get that P is on the tangent. We denote the tangent by AA. If and only if 2A is equal to P plus A square times the conjugate of P. Is this fine with everyone?
Can we use this like to show collinearity of any 3 points in general?
Not in any general 3 points. This only works on the unit circle. If it's not on the unit circle, because remember this foot of the perpendicular we defined, I only defined it for the unit circle. So without the unit circle, it would be way more complicated, but you could generalize it. Is that fine?
Yeah, okay.
Okay, now I move on to our first problem. I'll copy paste 2 problems. No, I'll actually just put one for now. Okay, so you can read the problem and think about it for a minute or so. Just know this is an acute angle triangle. Does anyone have any ideas?
So define the circumcircle as the unit circle and then calculate the argument of BAC by using those two.
Yes, that's the main idea. So if we set this to be the unit circle and O is the circumcircle, A, B, C, we have that AO we know is already 1. And if the order center has coordinates H is equal to A plus B plus C, we get that the argument of B plus C is equal to 1. Is that fine with everyone? Since the length of a segment AB is equal to the argument of B minus A. Is that fine with everyone?
Wait, why is that?
Okay, so let me just remember here how I talked about making it like a vector. So if we treat this like a vector, what happens when we treat this like a vector is that this has vector B minus A, and the magnitude of the vector will. Okay, wait, that's not the best way to explain. So let's say, and I'll just write it over here. B has complex coordinates x2 plus y2i, and A has coordinates x1 plus y1i. Now, if we go back to what these represent, we get that x1, y1, A, and x2, comma y2 for B. All right. So the length of this we know by distance formula would be root over x2 minus x1 whole square plus root over y2 minus y1 whole square. And also notice that this is the magnitude of a complex number with coordinates x2 minus x1 plus y2 minus y1 times I. Okay, and that's precisely B minus A.
Ah, okay, makes sense.
Okay, now can anyone tell me how to evaluate the magnitude of B plus C?
From here we can get angle BOC, since you know that B and C have magnitudes 1 and more magnitude of B plus C is also 1. So we get angle BOC to be 120, which is twice of angle A.
Wait, how did you get uh BOC to be 120?
Like if we draw the triangles, we know BO equals 1, CO equals 1, and like the vector sum of B plus C is also 1.
Mm-hmm.
So the angle between them must equal
You're
120.
doing trigonometry here. Like if these are the two vectors and this is the sum, you're using trigonometry if I'm not wrong, right?
Yes.
Okay, that's nice, but like any way to do it with complex numbers.
Rotate A or something.
What are you saying?
Rotate A.
Okay, that won't exactly work. Okay, so should I spoil the answer or should I let you come? Yeah, I'll let you guys think for a minute. Okay, so I'll tell you guys the answer now. The thing is, if the magnitude of B plus C is 1, we have that B plus C times the conjugate of B plus C is equal to 1. So this gives that B plus C times 1 by B plus 1 by C equal to 1, or B by C plus C by D is equal to -1. B square plus CB plus C squared is equal to 0. Okay, so now from here it's not so easy to get that angle BAC is equal to 60 degrees. What we can do is apply a nice trick by multiplying both of these by B minus C, both sides. So this would give that B cube minus C cube is equal to 0, or B cube is equal to C cube. Now, can anyone tell me the finish from here? Like how you can use this to get that angle BAC is 60?
We use the argument and expansion, the Euler form.
Okay, that's perfect. We get that if B is equal to E to the I theta. If I understand what you're saying correctly, we have that B cube is equal to C cube. So if C is equal to e to the I t, we get that e to the I into 3 theta is equal to C equal to e to the power of I times 3t. Okay, so now we want to show that so now directly getting angle BAC is hard, but we know that if B and C are placed on the unit circle and we want BAC to be 60, it's equivalent to wanting to show that the angle subtended at the center is 120. I think someone also mentioned this before. And now we use the idea of roots of unity. So there's this thing that the equation z cube is equal to 1 has 3 roots. One is e to the power of 0, which is equal to 1. One is e to the power of 2 pi I by 3, the complex number, and the other is e to the 4 pi I by 3. So this equation will, both of these equations give us that p is equal to some root of unity times c, w or w squared. And I'm writing the square in brackets since it may or may not be a square. And because of this, the angle subtended at the center would be 120. Since the argument of 2 pi by 3 is 2 pi by 3 in radians is 120 degrees. And whenever you're multiplying by a complex number of magnitude 1, you can think of it as rotating. So if B is here, by multiplying it by omega, we are rotating it 120 degrees on the unit circle. So this gives us that angle BAC is 60 degrees as desired. Now there's one small technicality here. What if the triangle looks something like this? This would give that this angle is 120 degrees. But the thing is, here, I mentioned that it's an acute triangle, acute angle triangle. So that solves the problem. Is that fine with everyone?
Yes.
Yeah.
Nice. Okay,
I
so now,
mean, the synthetic proof seems a lot more easier, but
yeah, synthetic proof is easier. But this proof is not actually complicated. So, my write-up for this proof is just like 2-3 lines. Like I was explaining all the details, but like as soon as you reach B cube is equal to C cube, you can just directly state that B is equal to omega times C. Omega is C times omega or C divided by omega. And then you can write it up. Like I'll share my write-up maybe, but like it's not that hard to write up.
okay, got it.
Okay. Also, if any of you have seen this before or you want a buffer problem, you can DM me and I'll put up some buffer problems. Then I'll put up the next problem. Okay, so you can read this problem and think about it for a while. Also, for those who want buffer problems, I'll be putting some up soon.
Could you zoom in a bit?
Yeah, sure.
Thanks.
Okay, I'll also be putting up buffer problems for those who have seen this before. Okay, also, I showed here how to get the foot of the perpendicular, right? So we have a segment AB, called AB of the unit circle, and the point Z. I showed the foot of the perpendicular. So this can also give the reflection of Z across AB. Since we get that Z plus Z prime is equal to the foot. So we can just solve for Z. Z plus Z prime by 2. We get Z prime is equal to 2F minus Z, and then we can just solve for it. So this is the note for those who are going to try the second problem.
Can you like zoom in? Because I still can't see.
Yeah, sorry. Can you see now?
Yeah, it's fine now.
Does anyone have any ideas?
Please wait for a second.
Oh, could you repeat? I can't hear you clearly.
I was just requesting you to wait for some time.
I still can't hear you. Can you talk a bit loudly?
I was requesting you to wait for some time.
Okay. Does anyone have any ideas?
We can find the value of D, E, F and then try.
Yes. Okay. So firstly, we want please we want the circumcircle of ABC to be the unit circle because then DEF would be neat. So A has coordinates A, B has coordinates B, and C has coordinates C. And now since A A prime is the uh diameter, we get that A prime has coordinates minus A, B prime has coordinates minus B, and C prime has coordinates minus C. Now, if P has coordinates P, we know by our for the perpendicular that D has coordinates B plus C minus no, B plus C plus P minus BC P conjugate by 2. We would have
Is- Isn't that if P lies on the unit circle?
no. The formula only applies for when B and C are on the unit circle. P can be
Oh, okay.
I proved it for the case when it was on the unit circle, but it can be anywhere.
Okay.
C plus A plus P minus C A is conjugate by 2. Okay. So now can anyone tell what the coordinates of X, Y, and Z would be?
So I found X is equal to A plus B plus C plus P minus BC P dash. I mean P conjugate.
Yes, perfect. So
And then everything else is just symmetrical.
yeah, we must use small letters. Now, can anyone see the finish from here? Okay, I'll come back in a second. I just have to bring my iPad charger. Okay, I'm back. So, in
We can do like x minus y by x minus z and get the angle, and it will be equal to.
okay, so wait, could you just repeat what he said?
We can do like x minus y by x minus z, and it will be equal to like sum of the.
Yes. So that's one way you can finish. So
Can you finish by the lengths instead of the angles?
yeah, both length and angles are a way to finish. But I showed the neatest way to finish. Um, so firstly, let's say we have x, y, z is a triangle. Now we know that. Let's say we translate this triangle, right? After translating this triangle, the triangle is still similar to its original thing, right? So
Yes.
now translating is just adding a complex number, right? Do you see why that's the case?
Yes.
Yeah, so if if you want to show that x, y, z is similar to ABC, you want to show that x minus a plus b plus c plus p, y minus a plus b plus c plus p, and z minus a plus b plus c plus p is also similar to ABC. Is this clear to everyone?
Yes.
And now this we know to be a negative of BC times P conjugate. This is negative CA times P conjugate, and this is negative AB times P conjugate. Okay. Now we do another trick. So, the thing is, if let's say how I subtracted this from everything, we also that if E is a complex number, X, the triangle XYZ is similar to x prime, y prime, z prime, where x prime is equal to x by a complex number t. Y prime is equal to y by t, and z prime is equal to z by t. Does everyone see why this is the case?
It's just a rotation or what?
Yeah, that okay. Remember how I said that when multiplying by a magnitude 1, it's a rotation? When multiplying
Yeah,
by
it just
yeah,
it dilates the triangle.
yeah, it scales and dilates and rotates, and it's also known as a spiral similarity, homotety, and the rotation. So now let's say we set T to be equal to negative ABC times P prime. What does this give us? We get that x, y, z is similar to the triangle of 1 by A, 1 by B, and 1 by C. The coordinates 1 by A, 1 by B, and 1 by C. Now, what do we know about 1 by A?
It's a conjugate.
Yeah. So we have the x, y, z is similar to, this is not exactly the best notation to use, but yeah. Now, is A conjugate B, A conjugate B conjugate C conjugate similar to ABC? It is right since we
Yeah,
are,
it should be.
yeah,
Like this
since
is minus A
beginning,
minus B and minus C.
beginning, we define conjugates to be a reflection over the y-axis, x-axis. So when you reflect a triangle, the two triangles are similar and you reflect one across an axis, they're still similar. Which finishes.
Okay, I didn't get it how you got A conjugate, B conjugate, C conjugate, conjugate as similar.
Okay, so did you understand why XYZ is similar to A conjugate?
Yeah, I got like till that, and then after I didn't get it.
So remember how we defined conjugate in the first place? We defined conjugate to be the reflection of a point over the x-axis.
Yes.
So let's say you have these two triangles which are similar, and you reflect this one across the x-axis, you get this. Clearly, this triangle would be similar to this triangle, right?
Okay, I got it, I think. Yes.
Yeah.
Thanks.
No worries. Okay, so now let's see from did any of you get any progress in this problem?
Could you like give us some time because I don't think I've drawn the diagram itself.
Sure. Oh, you can take 10 minutes or so, and then if anyone has ideas, you can say it out.
By symmetrical with respect to the line, do we mean like its image?
Yes, yes, the reflection of the point across the line. So if B is here and this is B, C, S should be here, the reflection. Is that fine?
Yes.
Is like the mod function distributive?
No. Because if you remember our example, we got that mod B plus C is 1, right?
Yes.
If the mod function is distributive, we get that mod B plus C is always 2, which is not always true.
Okay, got it.
Like also A and minus A, they have equal mods, but if we sum them up, the modulus is 0.
Yeah, understood.
The mod function is distributive in the special case when B is equal to some real numbers times A. Like, oopsies. When B is some real number times A, we get mod of B plus mod of A is equal to mod of B plus mod of A. And everywhere else, mod of B plus A is less than or equal to mod of B plus mod of A. Can you tell me why this is the case? Anyone?
I mean, they can either add constructively or they won't. So then it's the inequality.
Well, that's that's a nice intuition, but that's not exactly a rigorous proof because you just rephrase the statement.
We
What
can
about
put
like
B is equal to x plus iy, b is equal to, let's say, x1 plus y1I, and we will get that.
Yes, that's one way we could do it, but then there's also another way you could do it. So that's a way which has lots of algebraic calculations. But if this is the complex number A and we add B, this becomes the triangle inequality, which is exactly what Ohm said. Like, because the magnitude of A is the length of this, which is X, the magnitude of B is the length of this, which is Y. And if this is Z, the magnitude of A plus B, we know that X plus Y is greater than or equal to Z.
If I know that two lengths are equal, how do I compare them in complex numbers?
Could you elaborate?
Like if I say like there are points, say A and B and C and D, and I know AB is equal to CD on the geometric plane, then how can I state that in a complex number relation
So that's a
without
good.
using mod, if it's possible?
So B minus A is equal to. So we have that B is equal to CD. So you get
Yeah,
B minus A by C minus D. Its magnitude is 1, right?
yeah.
This gives that B minus A by C minus D lies on the unit circle. So
Okay, so Z
B,
conjugate is
yeah,
equal to Z, 1 upon Z.
yes. B minus A conjugate is equal to C minus D by B minus A.
Okay.
Oh, wait, so if you didn't understand the last step, basically the conjugate of this would be 1, the reciprocal of it, right?
Yeah, I'll be the reciprocal of it. That's
Does anyone want a hint on the problem?
Do we have conditions for concyclicity?
Okay, that's actually a good question. So I should have talked about this before. Thanks for reminding. Oh, let's see, we have 4 points. A. Okay, my pen's out of back. Okay, no, it's not out of battery. A, B, C, D, and now we know that if they're concyclic, then uh angle ADB is equal to angle ACB, right?
Yes.
So this gives that B minus A by C minus A and B minus 1 minute.
Not A.
No, I made a small mistake. C minus A by C minus D and D minus A by D minus B. These two have the same argument, right?
Yes.
So C minus A by C minus B by D minus A by D minus B belongs to the real numbers. That's the condition for concyclicity.
so this is like for any ABCD or like only on the unit circle?
Any ABCD. On the unit circle, on the unit circle, it would be the same. Yeah.
On the unit circle, you just have to prove that all the mods are 1.
Could you repeat?
On the unit circle, you only have to prove that the absolute value is 1, right?
Yeah.
Like all of
And
them.
yeah, and the way you do that is by Z equal to 1 by Z conjugate.
Okay.
So does anyone have any ideas in the problem? Okay, so this is a good point brought up on chat. Or There's also one way where the angles add up to 180. So here, if this is x and this is y, instead of x by y belonging to reals, we would have that xy will belong to reals. So if you want to check concyclicity, you have to check both of those, since one may not work out. Also, in general, if you want to prove concyclicity of 4 points, you have to be smart of which order you're doing it in. So here, I did C minus A and C minus B and D minus A and D minus B. But depending on the context, choose the points A, B, C, D, which reduces the calculations the most. So do you all want a hint for this problem?
Just a minute.
Okay.
Yeah, you can give a hint.
Could you repeat?
Can you give a hint?
What did he say?
Yeah,
Can you give a hint?
Yeah, give a hint.
Okay, so the thing is, this condition, AD parallel to BE parallel to CF, is hard to control. So
We can
that,
think like isosceles trapeziums.
okay, but hmm,
Convert them into lengths and then equate the lengths.
okay, but that would be very messy. So if you have A, B, C, you given that these lengths are parallel, right? We are DEF on the same circle. Yeah. So this is very messy since like the angles can be weird. So if you wanna eliminate the angles without loss of generality, we can say that we can rotate this to say we can rotate this so that it's all parallel to the y-axis. That's the brilliant thing, right? Since like, there's nothing wrong with doing it.
Oh, yeah.
Since,
Wow.
So all of them become conjugates of each
yes,
other.
And
perfect.
we could also like assume that C is on the y-axis. That yeah.
If you assume C is on the y-axis, then you can't assume the
Oh yeah. So
the other solution. So
I mean,
now
assume both, right? We just have to translate it.
then how
No,
will we become
okay.
conjugates if
conjugate
we
in the
don't
sense of,
assume that
Yeah,
the
okay, got it.
oh okay.
so now we get that D is equal to A conjugate. Wait, let me just move this frame down. Oh yeah, I'll actually just copy paste the problem on one. So D equal to E conjugate. E is also B, the conjugate of B, and F is also the conjugate of C. So now what can we see? Now we must calculate S, T, and U. So S, so firstly, let's say B, C are on the unit circle and X is some point. What would the reflection of this be? So the foot of the perpendicular we know is B plus C plus X minus BC X conjugated by 2. So the reflection will end up being B plus C minus BC X conjugate. And we can check this by the midpoint thing, right? Since the midpoint of this and
Yeah.
this should be here. So now S is the reflection of B on BC. So S is equal to B plus C minus BC D conjugate. But now we know that D is equal to A conjugate, right? So D conjugate will be equal to A. So which is this fine with everyone?
Yes.
Yes.
And now we find other similar.
Yeah. So D ends up being C plus A minus ABC, and U is equal to A plus B minus ABC. Okay?
But can't we just shift the whole consecutivity by A plus B plus C?
Yes, perfect. So
And with the minus ABC. Yeah, that's
so wait, we can subtract. So if we subtract ABC, we get that it becomes minus ABC minus A minus ABC minus B minus ABC minus C and 0. And we can negate to get that we're going to prove that ABC plus A, ABC plus B, ABC plus C and 0 are concyclic. Is this fine?
Yes.
Okay, perfect. So now let's say we put this as X, Y, Z, and U has already been taken. T is already, let's say, what's a letter that's not been taken? E. So let me just add a new form. We get that X minus Y by X minus Z is equal. Actually, no, let's make it in terms of E. So let's say X minus E and X minus Y is equal to AB.
You can also just shift it by APC and then it will become the unit circle.
Oh, yes, that's right. So we shifted by ABC, then we're done.
Yes.
So the main idea is, whenever there is something like which is hard to deal with, we can, without loss of generality, assume something so that it becomes easy to deal with. Now I will show. Wait,
One
before I
second. How do you
Yeah.
prove that minus ABC lies on the unit circle?
Okay, because ABC has a conjugate. So conjugate of oh no, conjugate of ABC is equal to conjugate
Conjugate of A and yeah, I think I got it. Yes. which is 1 upon A, 1 upon B, 1 upon C.
Yeah.
So when you multiply it, you just finish.
Yes, perfect.
Thanks.
Okay, now before I move on, I will show a very powerful formula. So say A, B, C, and D lie on the unit circle, and we wish to calculate the intersection of AB intersection CD, which is Z. Now, I will state the formula without proof, but I'll tell you guys how to prove it. So the formula for the intersection, we get that Z is equal to AB times C plus D minus CD times A plus D by AB minus CD. And the way to prove this is, we know that Z lies on CD, right? So I think we discussed this before. We have that Z plus CD Z prime is equal to C plus D. I proved this. I proved this somewhere over here. Yeah. Remember this? Is this fine with everyone?
Yes.
Okay, nice. So we know that Z satisfies this, and then Z also satisfies Z plus ABZ conjugate is equal to A plus B. Now, if we solve for Z, which I won't show, we'll get this. And now note that this is a very powerful formula in the sense that we can also get, if we plug A equals to B, we can get the intersection of the tangent with a random chord on the unit circle. And we can also get, let's say B is over here, A is over here, and we have these two tangents, we can get the intersection of the tangent. And this turned out to be 2AB by A plus B. Is this fine with everyone? Actually, I'll show the calculation on why this becomes the case. So if so I'll replace this with C. So we have that it becomes A squared times 2C minus C squared times 2A by A squared minus C squared, which is equal to 2AC times A minus C by A minus C times A plus C. And the A minus C's cancel out. All good?
Yes.
Okay. Okay, nice. So now now I'll give you time to try out a very nice problem, which highlights this important theme that while using complex numbers, you must not just directly go in and bash, but having a very good setup is very powerful, and making synthetic observations can be very useful instead of just going in and doing all the calculations. Can you all read the problem? Or you also in the book? Also, for those of you who want to refer to the solution later, this is Elmo 2017. This problem. Does anyone have any ideas? Like any ideas?
Let us finish drawing the diagram a bit.
Okay, sure. See, I'll just draw one diagram. Does anyone have any ideas? Like,
Okay, so the intersection of the circumcircle of ABC and the diameter of AH. So MH passes through that intersection. I hope you got it.
is this some geometry theorem? Since I don't know that many geometry theorems.
No, it's not a theorem. Like it's just angle chasing because
Yeah,
the reflection of H over M is the diameter.
yeah. I think I got the point.
Yeah, so then you can use complex, I think.
Oh, so think about what we want to prove. We want to do something about the order center of APQ. So,
Thinking of setting each diameter circle as the unit circle.
what are you saying?
I'm thinking of setting the other circle as the unit circle instead of the circumcircle of ABC.
Yes, that's the main thing. Since like, if we set ABC to be the unit circle,
Because
we
M is really easy to encode using P and Q because we know that from the P and Q formula you gave us.
how will we get M?
Like we won't get M precisely, but if we have like B plus C by 2, then we can find an equation in B plus C and B bar and C bar. I don't know how to proceed after that. I'm still working.
Okay, so that's a nice idea. So the main thing is we want to set, oopsies. You want to set APQ as the unit circle.
Oh, wait, and the reflection of H across the midpoint of PQ is the orthocenter of APQ. Oh, wait, am I wrong?
Oh, maybe, I don't know. Ah, yes, it is.
Yes.
Since I diameter stuff. Okay, so one thing is, let's see, we introduce E and F, where E is the foot of the altitudes. You know, the diagram's not so good. And now we do something magical, which is we set A, E, and F to be the free variables. Now, B and C are not free variables. We're defining the problem in terms of the triangle A, E, and F. Now,
One of P and Q will also be free, I guess.
what are you saying?
One of P and Q will also be free, I guess.
Yeah, we will define P and Q, but now we need to find something on M. Now, how will we get M?
Oh, we know B and C coordinates from that
Yeah.
theorem you gave earlier. So it's
Since
just B plus C.
we're trying to do everything on A, E, and F. So we want to find B and C coordinates, we'll have to write down equations. So
And H is just minus A in that unit circle.
yeah. So that's H is equal to minus E.
Actually, I don't remember any formulas, so I'm finding it a little difficult to,
Oh, what are you saying?
No, never mind. Never.
Oh, okay. So this problem, fine. Try thinking of a way to find m without formulas, like as less formulas as possible and calculations. Like, what synthetic properties do we know about m in this configuration?
Maybe we can use the fact that if we let AH, the foot of altitude, be D, then D, E, F, M are concyclic.
So you're saying that D, E, F, M is concyclic.
Yes.
Yeah,
Um,
9 point.
Uh,
Wait.
yeah,
Yes,
yeah, I
yes.
think so. I don't know of any like non-harmonic solution, but maybe.
Okay.
No, I don't think there is some harmonic.
No, there is no. I'm just saying for this property, I don't know a non-harmonic proof. But yes, it is 9-point circle. So now I got it.
Yes. So the main part, I guess, is like ME and MF are tangent to
Yes.
AEF.
ME and MF are tangents to AEF.
Oh, nice.
Do any of you know like this is a pretty well-known thing, so like
Yeah.
I encourage you to prove it by yourself.
Just angle chasing. So
Yeah, just angle chase. And noting that B is equal to MC is equal to ME equal to MF. That's one key step. So this gives that if we apply the formula we got before over that I've discussed over here, we get that M is equal to 2EF by E plus F. So now we can eliminate B and C since B and C don't matter to us. Now we just want to deal with P and Q. Now, oopsies, just shift it a bit. Now, what do we know about P and Q? We know that M lies on PQ. What can we say further? We can see that M plus PQ conjugate of M is equal to P plus Q, right?
Yes.
So this gives that P plus Q is equal to 2EF by P plus F plus PQ times the conjugate of 2EF by E plus F. Now, this gives that P plus Q is equal to 2EF by E plus F plus PQ. And now I won't go through all the calculations, but if I think it will turn out to be E plus F. We'll just show here. So for 2EF by E plus F, the conjugate is equal to 2 by EF by 1 by E plus 1 by F, which is equal to 2 by E plus F. This is fine.
Yes.
Okay, so now we get that the auto center of okay. So now we're still not done because we want to show that this orthocenter lies on the circumcircle of ABC. But before we can do that, we need to find the circumcenter of ABC, the coordinates. So how can we do that?
One second. How do you get P plus Q is equal to 2EF plus whatever?
Okay, so it's over here we know that M lies on PQ. So we get that M lies on PQ means that M plus PQ, M conjugate is P plus Q. Right?
Yes. Okay.
And
Collinearity
M
then.
is this, and then
Okay.
times M conjugate turns out to be this.
It
Okay. Got
also
it.
suffices to prove that that orthocenter, that ABC triangle's orthocenter and the midpoint are collinear, if I'm not wrong.
Could you repeat? I didn't hear it clearly.
I'm saying, I guess it also suffices to prove that the orthocenter of APQ is collinear with orthocenter of ABC and that midpoint of BC.
Maybe I do not know that much syntactic.
No, he just mean like the orthocenter is reflection about midpoint of PQ.
Ah, yes, it does suffice. So now, is there any smart trick we can do to calculate? Oh, like, wait, so let me just draw the diagram. Firstly, we've ignored B and C. Wait, no, now we can't ignore B and C fully, but if this is the midpoint, A, B, C, we have E is over here, F is over here, and H is over here. And this is the center of the circle. And we want to find the orthocenter O. So let's say the center is N, this is E, and this is F, and this is H, and this is O. Now, what can we see in this diagram? Know that N is equal to 0.
What do we need to find?
We want to find the coordinates of O. Okay, it's 7:30 now, so
So
class
I
should be over now, but I'll extend a bit longer, like maybe max 10 minutes. So what's one synthetic observation you can make about these
NH
points?
equal to OM.
What?
NH is equal to OM.
MH. Okay, why is that the case?
No, but it wouldn't help. So
Why is MH equal to 1?
NH equals OM. NH.
Okay.
But it wouldn't help. So
Okay, you're almost there. That's actually a very helpful observation. So should I say the observation or do you guys want to think about it for a second? Okay, so what does NH equal to OM give? Like,
NHMO is a parallelogram.
yes. But now the thing is, this wouldn't precisely be useful since we don't have the coordinates of. So now, just one thing. Let's say we have a parallelogram. We know that the diagonals bisect each other, right? So you notice, yeah. So we get that A plus C by 2 is equal to B plus C by 2. This is something
This
keep in mind.
yes.
Now, okay, so now back to the problem. Anything else you can see?
Yeah, so like we know n is now like
No,
center of
and
circle, and
Oh,
h
yes.
is like minus 8, so we can find O.
Yes, precisely. So we get that n plus m. Now n is 0, so we get that m is equal to h plus o. So o is equal to m minus h is equal to m plus a. Now, thus we get that o is equal to m was 2ef plus by 2. Now, can anyone see the finish from here? Okay, so let me just write down. Wait, this is a bit messy. So we got that the order center of APQ is equal to E plus. Let me just write this in red. And we got that the circumcenter and we want to prove that the order center lies on the circumcircle of ABC. So does anyone see how to finish up here?
I mean, the distance from O to the orthocenter of that triangle could be equal to OA.
Yes, that's what we want to prove. So the magnitude, the length OA is equal to the magnitude of 2EF by E plus F, right?
Yes.
And so the reason this is the case, since this is O and magnitude of the length OA is equal to the magnitude O minus A, which is 2EF by E plus F.
and we have to prove that this is equal to A plus 2PQ upon E plus F.
Yeah, sort of. So if this is, let's say, denoted by H prime, you want the length OH prime is equal to the magnitude of O minus H prime. Or wait, let's write H prime minus O, which is equal to the length 2PQ by P plus Q. Now, does anyone see why 2EF by E plus F and 2PQ by P plus Q have the same magnitude? No, this is not. See, this is my bad. This is P
E
plus F.
plus F on the bottom.
What are you saying?
Yeah,
Do you see why these two have the same magnitude? Exactly. EF, PQ all lie on the unit circle. So EF has magnitude 1, PQ has magnitude 1. So we get that 2EF by E plus F, the magnitude is equal to 2 times the magnitude of 1 by E plus F, since the magnitude function distributes over multiplication. And 2pq by E plus F similarly is equal to 2 times 1 over the magnitude of 1 over E plus F. And like, yeah, which is 2 by the magnitude of E plus F. Is this all fine? Is this fine with everyone?
Okay, you could even rotate the 2 points and then prove the magnitudes are equal.
Yes, we can also multiply and then show. Since like,
By the way, like why EF magnitude is 1?
oh, because E and F both lie on the unit circle.
Yeah, but they are not like conjugate of each other, right?
What are you saying?
Oh, okay, okay, now I understand. Yeah.
Okay, wait, I think I stopped sharing screen. Can you guys see my screen?
No. We'll share again.
Okay, but anyways, I think let me just.
Yeah, we can see your screen.
So this is one of the problems where setup can be everything. Like otherwise, without setup, the bash would be very, very painful. What you could do is ABC is the unit circle, and then P, and you define P, and then you define Q to be the intersection, which the intersection is not very easy to calculate. Then the orthocenter, for the orthocenter of a non-unit circle triangle, you have to calculate the circumcenter, which requires lots of determinants and long calculations. And then after that, you'll get some expression, and then you'll have to verify that the conjugate is 1 by itself. And then after that will also be quite a lot of calculation. So the main thing is in this, the setup simplified it a lot. Like if I was to write the solution up, the write-up of the solution is roughly about like a paragraph, like less than a half a page or so. So, and in general, there are some complex bash problems. Without a good setup, it can take 10 to 15 pages. And with a good setup, it can take just half a page. So whenever you're bashing, just don't shut your brain off. Like always keep on looking for synthetic things you can do to make your calculations easier. And sometimes bash can help motivate a synthetic solution. And if you ever get a bash solution, think about how can you translate it to a synthetic solution, since that's also very powerful.
Like what? What motivated you to like use complex here? Like there are more synthetic observations than complex, to be honest.
Okay, so at least I saw this in a complex bash preset, so that's what motivated me to do complex. And now, as soon as I saw the orthocenter of APQ, I knew that APQ must be taken to be the unit circle, since otherwise we will not be able to deal with it. And then after that, I realized that E and F could be very useful to calculate M, since the same day I was reading EGMO and like I saw the lemma, so that I did. And then I don't know, just some part just clicked into my head. Like as soon as you realize that M is equal to 2EF, then you're almost done. Then this idea of ANOM, or when I solved the problem, I did ANOM is the parallelogram, which I've also seen before. So these were standardish ideas for me.
So like sometimes complex like synthetic observation are hard to make. So
Yeah,
like if you find a good setup and like easy way to calculate, you like try complex. That's the main motivation.
Bash actually has requires lots of you need lots of good intuition to be very good at bash. Like the best of people, Evan Chen, if you see his bash solutions, they're very short compared to the average solution because he uses a very good setup. Like there's some problems the moment you see it, you're like, oh, if I was to bash this out, it would be 10, 15 pages. Evan Chen has a complex bash solution which is just half a page because of his setup.
Yeah, like you also need some like skill to make less bash.
Yeah, there's
Less
also this. Yeah, there's also this. I'll put some problems in the preset, and the thing is, in these problems, the main thing will be a good setup. Like without the good setup, then you're just dead. You can't solve it. Like also one thing in complex bash. Let's say you want to calculate the intersection of two circles. Now, what you could do is to set up an equation that the points that are on both the circles, we know properties about them, and then you solve it. Or the another thing you can do is you can introduce new points so that the intersections just become Spicing centers. And Spicing, there's a very neat formula for Spicing centers. So I'll also be providing a bunch of formulas and on the preset, and I'll also be putting a bunch of like problems that just calculate the coordinates of certain points, and to calculate it, you will require some smart tricks, which will be very helpful for practice. Okay, so I think that's over for the class. I'll stop recording.